First, thanks organizers for giving me a chance to talk here. So here is the several specialists and elliptic PD, so it's very happy to talk here. And today, actually, I present some, I think it's a new method, but maybe it's a well-known method, but is the way is a new. So, of course, some result is also very well-known, but if we have some idea from that, maybe we can apply it to the more diverse equations and involving some monotonicity of the coefficient. So I explain how can prove some well-known result, and of course some part is new, but is generally well-known. But this I will explain the how can understand the solution structure to using the method of phase plane. So my concerned equation is this. I only consider the radial symmetry case in entire space. So actually, and coefficient also radial symmetry. And of course greater than 3. And here K is non-negative and K is bounded continuous function. But for simplicity, I assume the boundaries. But generally, we can consider the case in near KR as dr is finite. Okay. So, and of course here P is greater than 1. The theorem is this. First case, P is greater than n plus 2 over n minus 2. Usually we call that this case is a supercritical case. And of course it's a critical solver exponent, and the K is decreasing. And the second case is n over n minus 2 belong to this range, and K is increasing. Then there exists only one and only one singular solution, singular radial solution. And so I only consider the radial solution just if radial form is this one. Okay. So singular solution with slow decay. Here, singular solution means that limit r to the goes to 0, u r is infinite, and slow decay means infinity r to the 2 u r is also infinity. So let me remark something, because it's some cases very well-known fact. first I would like to mention about the regular solution. So it's a continuous, including the 0 point. Of course, it's a bounded continuous function, so it's a C2 solution. And first one is positive solution for the supercritical case with slow decay. And for the supercritical case is a supercritical. This is a supercritical, is a subcritical. We call that. And
is the limit is 0 or infinite?
Infinite. So some cases, this is converts to a finite positive constant. We call it the fast decay. Okay. And non-existence of positive solution for the subcritical case. Is already well known for if we assume that the differentiability of K and rate and also Einstein proved that this case proved by using the positive identity. So B and non-identity. And we exclude the case, critical case. So very subtle. So the long result is P is n plus 2 over n minus 2. And K is identically 1. It's very well known. All because it's 1 and all positive solution radially symmetry, and every radial solution has the fast decay. Positive solution with fast decay is proved comparative as block and the rate right. Okay, so B, the second case, K is not identically 1 and decreasing. Is a positive solution with slow decay. So we can regard that case, we can regard the problem as a supercritical problem because the structure is this case is all positive solution with slow decay. So actually this case is not a real critical problem. It's some kind of a supercritical problem. And increasing case is there is a non-existence. Of course, that factor already, this case is proved that the researchers. So, in some sense, it's the critical case. In some sense, the problem is a little bit changing. The main technique is a positive identity. So, I will explain how can prove that this one is more. Actually, we even though the result is very well known, but we want to know the more direct proof or the proof which can give us some way to see the problem. So very easily to understand why this phenomenon happened. Okay? So, second one is this one. Second, K is identically 1. Then the typical singular solution is this one. Yes. L is some constant. Of course, this one is positive only when if P is greater than L over N minus 2. Because it's the non-existence of this case less than this exponent is rather easy to prove. For example, K is identical 1 is very easy. So it's a non-trivial case, of course, there's this rate. Yeah. Last one is this one. For the singular solution, for L is equal to 0 and K is C1 and K is less than 0, decreasing case, and K is 0. This case is studied by Johnson and Fan and Lee. They used the invariant manifold theory, so they proved that. For the uniqueness for this, of course, they also consider the uniqueness. Greater for the general case, R is great. Oh, yeah. Actually, for the simplicity, I assumed that the K is bounded case. But in all stories, there are some stories for this case. When we here, if we little bit improve this case, R to the minus L is K is decreasing. L is here is greater than minus 2. This very closely related to the integrability of it. Okay? So we can for this case is L is increasing. So in this, for that case, the R is differently here and here. Okay. For that case, L is equal to 0. They studied there, and later for the general case, and was some differentiability and the convergence, some kind of convergence. They proved the uniqueness considered by uniqueness of the singular string. By Lee, and okay. So finally, the theorem 2 for the P is critical case. In this case, actually, there are continual singular solution. So, and all is a slow decay. K is decreasing. And then if this continue singular solution is slow. Actually can be characterized like for like this, given L1 D1 less than D2. So singular solution. Here and S L is less than that. Here, limit should. So to understand that why there is a difference of two problems, we can check that some kind of some kind of transformation called the power transformation, and then we can see that one. We can imagine that maybe that happened. So final remarks for the theorem. L, K here is less than 1, or this case for L minus 2. And P is greater than or less than N minus 2. Then we can easy to check this one. Minus 2 K R. This term appears in a quasi-binet. So, is for the simple case for satisfying this identity inequality, then we can understand some structure. And also this condition is equivalent to the K. Here is K is less than 1 equal to. So this condition corresponds to the critical case. When we let L like this one, P is N minus 2 here. So the condition monotonicity in some kind of a very natural condition to understand attack the problems. Okay. So now, just for the regular case, even though we can only consider the proof of regular case, we can understand the method of it. Because it's of course I have to mention that because it's not autonomous case, but if K has some kind of monotonicity, then we can apply the method of phase plan to understand the structure. Okay, consider regular case. So for initially you have the alpha here, positive alpha. Then because K is non-negative, is decreasing as long as it exists. So because it's some kind of the nonlinearity, actually even for the case K is identically 1, then there's some scaling structure. So it's very natural to using that structure. Then if Vt, let this one T is rho 1. So T is go to minus infinity as R goes to 0. This V satisfying this. here A is equal to n minus 2 minus 2n. Is easy to check that is the greater than or equal to 0 if and only if t is, but for the general case, of course, the 2l n minus 2. Of course, we only consider this case. So, critical case is 0. So maybe some kind of oscillation may happen. Yeah, that occurs this way. So to apply the page plan, let V is a T. Then V is equal to Z as V. Of course, T goes minus P. And at infinity, because it's a here small k is R3 minus L is K. So you can easy to see that at minus infinity, QV near minus infinity is greater than. Yeah. So the page plan start here and then going up. And then maybe some cases turn back here, but recently over is over the past 10 years is some cases does not hit here, just stayed up halfway. Well, P is greater than PC. PC is depend on Ln, and this is greater than another critical number. Good. So the other case, P is P of less than this number. There's some point. Have to hit the axis here, V. So we can page plan maybe touch here and or touch here is here. Okay, let the graph of a half plane we let Q, and the lower part is let Q, capital Q, and we can define the small k1 here, and here k2. So suppose we claim that for the supercritical case, and K is decreasing, this shape have to happen. The other case leads to the contradiction. So suppose like this one or this one. Okay, let that happen T1. And then we integrate that one, that equation. Then from here to there, V bar, and A V and lower part and then we can have this one. here disappear this one and only K2 minus K1. So first case, A is positive. Of course, it's a supercritical case, A is positive. And then let the, this term is let the I is the second one, this like this. Then this case is positive. Of course, this is a positive function, so it's positive, and is also positive. So this greater than that, but second one, right hand side here is because it's a decreasing, so it's a that's the contradiction. Second one, A is identically 0 is a critical case. Critical case may be T1 here happen plus infinity. Then it means that at plus infinity the solution goes to 0 and the derivative goes to 0. So you can need to see that is a Q0 is 0. So this one, A is 0, Q is 0, then is 0. But to obtain that we assume that P is a critical case, we assume that K is not identically 0, a constant, then this term is less than. If K is not constant. Okay. So T1 is less than finite point, then Q0 is less than 0. Because it's a unique of ODE. In some cases, we can have that U prime R is 0, U R is 0. So solution must be identical. So we can have this. So this case, like this, is also contradiction. Okay. So this orbit should be have to have this shape. So apply the same technique, then local minimum point is increasing. So it means that the solution is has a slow decay, trivially, obviously. So is the very easy to see that what happened for the of course when you are using the same technique, you can have the structure for the subcritical case because the sign is changed here. Subcritical case and A is negative. So you can have the non-existence of positive solution. Let now think the singular case. First observation is this one. Is K is identically 1, then is the single solution we already know, like this one, and sometimes. And first observation is this one. K converges see, of course, for simplicity 1 as at 0, the k, and the k is decreasing. Then any singular solution should be greater than L. Because we already know that the local minimum point is increasing. So if you in here L here, or some singular solution has some point, the orbit has some point here, then as the local minimum point is decreasing, if we shift to the backward, but is start on somewhere, some start there, as a limit is impossible because it's from the equation. So you convert to here, and that case is to using another technique, you can prove that is not singular, it's a regular solution. So very important observation, this one. Okay. So when k is identically 1 near 0, is a trivial case because it's okay. So for the, if you at phi r define like this one, then phi r satisfies a plus 1. So, and let RC is infinite. Here, of course, if we near 0, so we escape the singularity here. Because if we can define some solution, we already know that this is a solution of near 0. And then locally, because it's a regular problem, so we can push it further. Actually, then this solution should be slow decay entirely, going further and further. So it's a trivial case. So the other case is k is to 1 at 0, but RC here is equal to 0. Actually, we have some uniform estimation of the for the singular solution, because in a phase equation there's upper bound. So we can, using that kind of estimation, we can prove the if you the k is like this one, and then we consider for this case. We have already know that from first case we have a singular solution, and then later another singular solution. We can, using that kind of singular solution, as actually convert uniformly into some singular solution of this one. So uniqueness is also very interesting, but the proof is very simple. Because there are two solutions. A is positive case. R two solutions. From two solutions we define phi 2, phi 1. And then two solutions converge to L have to converge L at 0. So here is apply that some invariant theorem here, phi 2 minus phi 1, and here 1 plus. is some singularity, but if you has a phi 2 is greater than phi 1 is positive, but is a negative because this at near 0 is converged to L, it is equal to this one, but this P is greater than 1. So it's negative. It's positive, impossible. Okay. So have to oscillate here, but this is also impossible because we have some two consecutive zeros. That is 0, but near 0 is not 0. So uniqueness is very natural. So even for in case. So for the remaining situation is that we have to find some, for the critical case, we have to find some kind of okay, for A is a critical case and K is identically 1, the orbit like this one. Regular solution only this one. And the singular solution L here, another singular solution structure like this one. Actually call that Drouin Fowler type is some kind of. And each point has some periodic solution. This is very well known. But K is monotonically decreasing and critical case, then using this one and then compared to the same idea applied to that, then I can prove the same structure for the singular solution. So in some sense, K is decreasing. The critical case, of course, critical case, the structure does not change because it's the same structure. So I suspect that K is not assumed that K is decreasing, only decreasing, and P is n minus 2. Then even this case, there's only one and only one singular source. Actually, this is a remaining question. So in this, without, no, I mean it's a K limit KR limit R goes to 0 is empty. So for the regular case, P is critical and P is critical, then some kind of monotonicity change very rapidly the structure of the regular solution structure. But the singular solution case, when at 0 as infinity, then these problems turn to the supercritical problem, because in this supercritical case is has only one and only one singular solution with the slow decay. But this I don't remark. I did not mention the supercritical case. We can use because we have a singular solution with the slow decay using the Kelvin transform. Is also singular solution with the slow decay for the subcritical case. Yeah. So my final remarks, this one is maybe of course I studied but local monotonicity at, for example, near 0 at infinity, and then we can understand usually, and I can also see that some structure for small initial data, very large initial data. Then we just using the scaling, then we understand the structure. For example, for the critical case, in a fixed R is some kind of K is like this one. Here in the boundary a little bit increasing, then there is some solution. Critical case. Of course, here is a trivial. Is a boundary case of that. And I have to mention in this case, the existence of singular solution already for the very large P is some PC is studied by with Chan. And I think for the even for the regular solution structure, even Gaussian curvature, of course, generally that Gaussian curvature only consider dimension is 2, but it's generally general dimension. Because it's equation fixed, the solution, the criticality is changes according to the dimension. So that case may be applied to that. Okay, then start.